about properties of logarithmic functions, and further, how we can expand them, but better yet, how we can simplify them. Let's first take a look at the middle column here when we look about our laws of exponents. These are laws of exponents we've used many times before. And since logs are just another way to write an exponent, they follow the same rules. So if I'm multiplying my logarithm, I'll end up simplifying or expanding by adding them together. I can simplify them through subtraction to create a division. When I have a logarithm to a power here, I can bring that power out front. And this becomes one of the most useful properties of logarithms. We've already discussed that log base 10 of 0 is 1. Similarly, the 0 property itself is x to the 0 is also 1. And how we can write negatives. If our negative is out front, we can bring that negative up to the top, so going backwards from out front up top. And then we can rewrite that negative exponent as 1 over x. The laws have to have the same bases. So let's express as a sum of logarithms. Notice here that I have log base 3 of 9 times 27. Here I'm multiplying my two values on the inside. And since I'm multiplying those two values on the inside, I can rewrite them using addition. Therefore, log base 3 of 9 times 27 is the same as log base 3 of 9 plus log base 3 of 27. Here we're expanding. Example 2, express as a single logarithm. Here we have a couple things happening. First of all, I have this addition piece, which means that I'm going to multiply my pieces together. And by multiplying my pieces, I mean these portions here. So I'll keep the log base 2, but now we will have p cubed q, simplifying our logarithm. Let's express log base a of 11 to the negative 3 as a product. So as a product, I have an exponent that's on the outside, which means I can use the power rule and bring it out front to give me negative 3 log base a of 11. Let's express log base a of the fourth root of 7 as a product. I can rewrite my exponent. Right now I have it as the fourth root. I can rewrite this as 7 to the 1/4 power. Inside over outside. This is the same then as log base a of 7 to the 1/4 power. Using the power rule, I can bring that exponent out front so that I have 1/4 log base a of 7. Let's express the natural log of x to the 6th power as a product. Very similar to the logarithms, the natural logs follow the same rules as well. So I have an exponent that I can bring out front. So this then becomes 6 times the natural log of x. Let's go backwards and expand. Right now I have the quotient rule, and the quotient rule says that I can divide, the quotient rule tells me that we can subtract them. I will have then log base t of 8 minus log base t of w. Or going backwards, I'm in subtraction, they have the same base. I could also rewrite this as log base b of 64 over 16. However, I can simplify 64 over 16 to provide me with log base b of 4. Let's express log base a of x squared y to the 5th over z to the 4th in terms of sums and differences. So we want to expand this. The first thing I'm going to do is notice that we have this division sign here. So we're going to use the quotient rule first. The quotient rule says that I can subtract my denominator from my numerator. That will provide us then with log base a of x squared y to the 5th minus log base a of z to the 4th. So I started with my quotient rule. I now have a power rule, a product rule, because I'm multiplying x squared times y to the fifth. So I'm going to use the product rule to separate. When I separate, then I'll have log base a of x squared plus log base a of y to the fifth minus log base a of z to the fourth. The last thing we can do is use the power rule for each one of our exponents, bringing them out in front of the logarithm, providing us then with 2 times log base a of x plus 5 times log base a of y minus 4 times log base a of z. Here I have log base a of the cube root of a squared b over c. What I'm first going to do is rewrite this. This is all to the first power, so I'm going to rewrite this so that I have an exponent of log base a of all of our insides to the 1/3 power, inside number versus the index. I'm then going to use the power rule and bring that 1/3 out front. So I have 1/3 times all of this stuff here. I then am going to use the quotient rule to break apart that division into subtraction. I'll then have 1/3 times log base a of a squared b minus log base a of c to the fifth. Then I'm going to use the product rule to separate these into addition. Log base a of a squared plus log base a of b minus log base a of c to the fifth. Finally, I'm going to use my power rule and bring all of my powers out front of the log if they have them. So 1/3 times 2 times log base a of a plus log base a of b minus 5 times log base a of c. Finally, distributing the 1/3 to each logarithm here provides us then with 2/3 plus 1/3 log base a of b minus 5/3 log base a of c. But you're probably asking, where did that first logarithm go? Remember, we have log base a of a here. And from our rule from last time, if we have log base a of a, its result is 1. So this whole piece is the same as 1. So really, I just have 2 times 1 or 1, and 1/3 times 2 is 2/3. So keep those rules handy from the last time. Let's keep expanding here. Let's express log base b of ay to the fifth over m cubed n to the fourth. I'm first going to use the quotient rule and separate them into subtraction. So I'll have log base b of ay to the fifth minus log base b of m cubed n to the fourth. I'll then separate using the product rule into addition. So I'll have log base b of a plus log base b of y to the fifth. And if it helps you to keep these in parentheses, please do so. And then I'm going to subtract everything on the right. I'm subtracting all of these items, so be careful with your subtraction. I'll now have log base b of m cubed plus log base b of n to the fourth. I'm going to distribute the negative, providing us then with log base b of a plus log base b of y to the fifth minus log base b of m cubed minus log base b of n to the fourth. And finally, using our power rule, I'll still have log base b of a plus 5 times log base b of y minus 3 times log base b of m minus 4 times log base b of n. None of our logarithms are the same, so we have to keep them here. We have to keep them expanded, but there's nothing that we can combine. There's no like terms. Let's go backwards. Let's say we're given a huge long logarithm, and let's simplify into a single logarithm. Just like the last thing I do is use the power rule, I'm going to use the power rule to put those exponents back where they belong. So I'm going to put this 5 back with the x and this 1/4 back with z. So I have log base b of x to the 5th minus log base b of y plus log base b of z to the 1/4. The first operator I see is subtraction. That tells me that I can take that subtraction and put it into a quotient using the quotient rule. Log base b of x to the 5th over y. I know that I'm going to be multiplying, but I also know that I can rewrite z to the 1/4 as the 4th root of z, since it's z to the 1st power. And since I'm adding, I'm actually going to be multiplying. So multiplying, and this is over 1. So when I multiply this, I'll have x to the 5th, the 4th root of z, all over y. Example 8, let's express this as a single logarithm. Since I'm in subtraction, I know that I can write it as the quotient. So I'll have the natural log of 3x plus 1 over 3x squared minus 5x minus 2. Let's go ahead. I'm suspicious that we can factor that denominator. So what multiplies to -6 and adds to -5? -6 times 1 does, providing us with 3x squared minus 6x plus x minus 2. We have 4 terms, which we'll factor by grouping. The first 2 are divisible by 3x. So when I divide by 3x, I'm left with x minus 2. Nothing is divisible in our second set, so I'll divide them by +1 to keep the x minus 2. We now have the common binomial of x minus 2, and when I factor out x minus 2, we'll have 3x plus 1. I notice now that I have a common binomial in my numerator and denominator that we can simplify, leaving us with 1 in our numerator and x minus 2 in our denominator. Here we have, given that log base a of 2 is approximately 0.301, log base a of 3 is approximately 0.477, find log base a of 6 if possible. And I'm going to put here that we only can use log properties here. So if I'm looking for log base a of 6 and I have to put it in terms of 2 and 3, I know that log base a of 6 is the same as 2 times 3. Using the product rule, I then can take log base a of 2 plus log base a of 3. I know what log base a of 2 is, and I know what log base a of 3 is. And so I can easily add them together for 0.778. We have the same log base a of 2 and log base a of 3. It's asking us to find log base a of 2/3 if possible. Well, I know that 2/3 is the same when I use the quotient rule as log base a of 2 minus log base a of 3. So I can subtract log base a of 2 and take away log base a of 3, providing us with approximately negative 0.176. Sometimes we have to get a little creative with how we operate these. I'm looking for log base a of 81. I know that 81, and I'm thinking in terms of 2 and 3 here, I know that I can rewrite 81 as 3 to the 4th power. I also then can use my power rule and bring this down in front, which just simply means 4 times whatever log base a of 3 is, or 4 times 0.477, which is about 1.908. Example D, we want to know what log base a of 1/4 is if we're able to find it. Here we're dividing, so we can use the quotient rule to turn into subtraction. That would give us log base a of 1 minus log base a of 4. Also, we have ourselves a rule. Log base a of 1 is 0 because when I take a to the 0 power, I get 1. So I can replace log base a of 1 with 0. I also can replace 4 with 2 squared, so now I'm written in forms of 2. I can bring my 2 out in front of my logarithm so that I have -2 times log base a of 2, or -2 times about 0.301, which gives me approximately -0.602. So you sometimes have to be a little creative with how you're going to rewrite these. Again, we have the same log base a of 2 and 3. We want to find log base a of 5 if possible. The only thing that I could think of would be that I could take 2 plus 3, and that would give me 5 when I'm written in 2 and 3. However, that does not equal the same as adding them together. That's not the product rule. So there is going to be a couple of instances where it is just simply is not possible. And finally, given that log base a of 2 and log base a of 3 have been what we're looking for, let's find what is log base a of 3 over log base a of 2. It's already written for us, so all we need to do is replace our log bases with their decimal form and divide and get approximately 1.585. All right, let's simplify here. Here I'm looking for log base a of a to the 8th is what? So I'm looking for what power can I bring a to? So a to what power would give me a to the 8th? Well, that's simple. We would need to have 8 up here so that they would match. Similarly, here I have the natural log of e to the -t. We know that the natural log of e is the same as log base e times of e to the -t. So I'm looking for e to what power would give me e to the -t. Well, of course, I'd have to have -t then. Similarly, log of 10 to the 3k is what? If we don't have a base written, we assume that the base is 10. So I'm looking for 10 to what power gives me 10 to the 3k. And of course, that would be 3k. So what we've found here is a rule that for any log base a and any real number x, whatever that might be, that if I have log base a of a to the x, it equals x. Similarly, if we have a base to a logarithmic power, so if I take log base, or if I have a to the power of a log, notice that as long as the bases are the same, they end up canceling and all we're left with is x. So here 4 and 4 are the same, they end up canceling, so all we're left with is k. E to the natural log of n, we know that e is the same, or natural log is the same as log base e of the 5th, so now our bases match, so I have 5. Even though I don't have a base with my log here, I know that it's automatically 10. They match, so this is the same as log base 10 of 7t. Since they match, they cancel, and we have 7t. Now that we're familiar with some properties, the next lesson will be how do we solve logarithmic functions.